Okay, we're going to take a look at section 13.1, and this chapter deals with probability. So just a quick little history on probability. It originated in the 16th and 17th centuries in Italy and France, and it actually came about in a question that Pierre de Fermat posed to Blaise Pascal about gambling. He was wondering if two people were playing a card game and it ended early, who would get the winnings? Blaise Pascal was a French mathematician, a physicist, an inventor, a theologian. So like many of the mathematicians we looked at in Math 103, he studied many different fields. His biggest contribution to mathematics was Pascal's triangle. Pascal's triangle is used to do some expanding of binomial to a certain degree. And it's also used in looking at combinations and permutations. Pierre de Fermat was a very influential mathematician as well. He studied law prior to mathematics. He made lots and lots of contributions to the field of mathematics in geometry, calculus, and number theory. And he actually posed a question or made a statement as a side note in a book that he was reading about a theorem that he thought he could prove, and he jotted it down but never proved it. And Fermat's theorem is a theorem that took hundreds of years to prove, and it was proved in 1994, I believe, by an American mathematician. How is probability used today? So probability is used quite often, and that's why we're actually going to study it first. We hear many things or see probability in many different ways. When we look to see what the weather is going to be like and we see chances of rain or chances of snow, we see it in batting averages, we see it in lotteries and the probability that you'll win a lottery. Elections, when we have polls and they predict who the winners will be, and then also in standardized scores. So what is probability? The definition of probability is the extent to which an event is likely to occur. So in the early grades, 3rd, 4th, 5th grade, when we talk about the probability of events, typically students will respond in words like it's certain to happen, or it's likely, unlikely, or impossible. Typically there's not a numerical value that they're using. They're just using terms like certain, likely, unlikely, and impossible. When we get into 6th, 7th, 8th grade, that's when we start to do some calculations with probability. And we know that the probability of an event is going to be a number between 0 and 1, or that it's a percent chance between 0 and 100% chance. So when we talk about something having a 0% possibility of happening or has a 0 probability, it means that it's not going to happen, that it's impossible. If something has a probability of 1 or 100%, it means that it's absolutely certain that it's going to happen. To calculate a probability, we need to learn a couple of terms. Those terms are sample space. So a sample space is the set of all possible outcomes. Event is a subset of that sample space. And then the probability of an event is really going to be the fraction or the ratio, and that's the number of outcomes in event A over the number of total outcomes in the sample space. So I have a picture of a standard die off to the side here, and the sample space for a standard die would be all the possible outcomes you could get if you rolled a standard die, and that would be 1, 2, 3, 4, 5, 6. Then I created an event. The event I created is rolling an even number. So the possible outcomes in rolling an even number would be the numbers 2, 4, 6. So the probability of event A, the probability of rolling an even number, would be 3 outcomes out of 6 outcomes. So 3, 6, which we could reduce to 1/2 or the decimal 0.5. For a probability, you can either write it as the decimal 0.5, or you could write it as the percent, 50%. So there's a 50% chance that I would roll an even number if I was rolling a standard die. Let's do a practice problem here. So we're going to determine what's the probability of rolling a number less than 3. So what we want to do is we're going to go ahead and create the sample space. And because it is a standard die, that sample space is going to be the same as the one we have above. Our possible outcomes in our sample space are 1, 2, 3, 4, 5, and 6. Then we want to create the outcomes of event A. For event A, we're looking at a number less than 3. So my possible outcomes are going to be 1 and 2. Those are the numbers less than 3. So the probability of rolling a number less than 3 would be 2 outcomes out of 6, which reduces to 1/3, which would be the same as 0.3 repeating, or a 33 and a third % chance. Let's look at another example. This time, instead of looking at a standard die, we're going to look at a coin. And suppose that we're going to be tossing 2 coins. And we want to determine, if we're tossing 2 coins, what's the probability of getting 1 head in the tossing of 2 coins. So for example, what I have drawn here, I have 2 coins and 1 head appears. So first I have to think about the sample space. What are all the possible outcomes I could have if I'm tossing 2 coins? So I could end up with getting a heads, I could get a heads, tails. I could have a tail heads or a tail, tail. I have a total of 4 possible outcomes. Depending on what our devices that we're using to find our probability, sometimes we can generate the sample space by just listing out possibilities. Sometimes we might need to create a tree diagram to help us with it. So for this one here, tossing 2 coins was not a difficult one to generate all the possibilities, but if we were tossing 3 or 4 coins, it might get a little bit more difficult. If you were to create a tree for what we have here, our first toss would be, you could have tossed a head or you could have tossed a tail. My second toss, if I tossed a head, the second toss could have been a tails or a head. Had my first toss been a tail, my second toss could have been a head or a tail. And then from there, if you follow the pathways, I could follow this pathway and I would have had heads, tails. If I went this route, I had heads, heads. If I went this route, I'd have tail, heads. And finally, I could go tail, tail. So you can generate your sample space either way. But I can tell right now that the number of outcomes in my sample space is a total of 4. So then my event is tossing 1 head. So I can see from my sample space that there's just 2 times where I would end up with exactly 1 head there. So I have heads, tail as a possibility and tail, heads as another possibility. So the probability when tossing 2 coins of having exactly 1 head appear would be a total of 2 outcomes out of 4 outcomes, which is the same as a half or 0.5 or a 50% chance. All right, let's look at another example. Here we have a spinner, and the spinner has several different colors on it, and we are looking to determine what the probability of landing on the color purple. So we need to first figure out what our sample space is. And I can see in my sample space that I have a variety of colors. And so what I'm going to do is I'm going to list out my colors. I'm going to start here and go in the clockwise direction. So I have red, purple, red, yellow, purple, blue, purple, yellow. So that's my sample space. I listed out all the colors, the number of times they appeared. 1, 2, 3, 4, 5, 6, 7, 8. I have a total of 8 colors in my sample space. So then I'm looking at the probability of landing on purple. I can see in my spinner that I have 1, 2, 3 possible outcomes, 3 times that I could land on purple. So when I calculate my probability, it's going to be the number of possible outcomes, so there's 3 ways for me to land on purple, out of a total of 8 different color choices. So my probability here is going to be 3/8, which is the same as 0.375 or 37.5%. So there's a 37.5% chance that I would end up spinning the spinner and landing on a purple. One more example here. We're going to take a look at rolling 2 standard dice and trying to determine the probability of rolling a sum of 7. So to calculate or to figure out what the sample space of 2 standard die, what we have to think about is that we know the possibilities for 1 standard die would be 1, 2, 3, 4, 5, 6. The same is true for the second die. 1, 2, 3, 4, 5, 6. So when I roll 2 standard dice, the possible outcomes I have would be I could roll a 1, 1, I could roll a 1, 2, a 1, 3, a 1, 4, a 1, 5, a 1, 6. My first die could be a 2, and my second one could be a 1. It could be a 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. We're just going to continue filling in this chart, and what we're going to end up with is a total of 36 possible outcomes in our sample space. Now, it would be difficult to list out all of these in the sample space, so I think once you make one chart of these, you can refer back to that chart over and over again. I made an error here. This is supposed to be a 3, 4. So we have a 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. Total of 36 possibilities there. And then I want to look at event A is rolling a sum of 7. So we need to figure out how many outcomes are going to give us a sum of 7. So if I look here, I can see that 6, 1 would give us a sum of 7, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6. It's actually a diagonal here of possibilities here. So I have 1, 2, 3, 4, 5, 6. I have 6 ways to make 7. So the probability of rolling a 7 would be the number of outcomes in event A, which we said were 6, over the total number of outcomes. We said there were 36 possible ways that we could roll 2 dice, which would give us an answer of 1/6. And then we would go ahead and calculate what that percentage is. I don't know what that is off the top of my head, but you guys have a calculator that you can go ahead and look at. Okay, and number 4, we're again going to look at those 2 standard dice. So we're going to be able to look at the sample space we have already created. And here we're looking at what's the probability of rolling a product less than 12. So this time we're looking at a product, which means it's multiplication. So if we were to multiply the 2 numbers on the die, we would end up with a product less than 12. So again, we know that our sample space is going to be 36, and what we need to figure out is what is the number of outcomes that would be less than 12, a product less than 12. So here I can look at, I know 6 times 1 is less than 12, 6 times 2 is 12, it has to be less than, so I'm going to go up here. 5 times 2 is 10, but 5 times 3 is 15. 4 times 3 is 12, so I'm not going to do that one. 3 times 3 is 9. 2 times 4 is 8. 2 times 5 is 10. And then I have 1 times 6. So I believe everything to the left here, this is going to give me 6, 5, 10, 8, 4, 3, 6, 9, 2, 4, 6, 8, 10, 6, 5, 4, 3, 2, 1. And then all the other values that I don't have marked in yellow are going to be numbers bigger, or products bigger than 12. So now I'm just going to count up how many items I have. So I have 6 plus 5 is 11, 12, 13, 14, 15, 16, 17, 18, 19. I have a total of 19 out of 36 possibilities. 19 out of 36, we need to go to our calculator and figure out what that decimal is, and then figure out our percent. So we've looked at how to calculate a probability, and what we've looked at is the theoretical probability. So that's in a perfect world, if our dice were rolled perfectly and they weren't being hit, or they were being shaken up the right amount, this is what we would expect in theory to have happen. So the theoretical probability tells us how likely an event is. It describes on average what happens in the long run. So in theory, if we were to test this out hundreds and hundreds of times, this is what we would expect to happen. Experimental probability shows us exactly what happens when we're conducting a simulation or experiment. So for example, if you were to toss a coin, you know that in theory, if you're tossing one coin and you wanted to find the probability of tossing a head, it would be a 1 out of 2 probability. It should be a 50% chance. However, if you were to toss a coin 10 times, or 20 times, or 30 times, you might not get it to be exactly that 50% probability. I conducted an experiment where I tossed a coin 50 times, and when I tossed that coin 50 times, I ended up getting heads 29 out of 50 times. That gave me an experimental probability of 58%. So if all of us tossed a coin 50 times, we would get a variety of different values, probably some somewhat close to 50%, some higher, some lower. But if I was to take everybody's coin toss and we were to average together all of the probabilities, it would be a lot closer to 50%. So even though it's our theoretical probability that we expect it to be 50%, it doesn't always happen when it actually is simulated or as an experiment, unless we do it many, 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 many times. In class on Wednesday, we're going to take a look at how to conduct some simulations to determine probabilities. We'll make some comparisons between an experimental probability and the theoretical. So we'll create the simulation, get our data, and then compare it to what the theoretical says. But we do have a theorem called the theory of large numbers, and that tells us that if we conduct the experiment enough times over a long enough period of time, we would expect the experimental to reach what the theoretical is saying. Okay, so that is it for now. What you can do is go to the Nearpod link that is in Moodle and answer a couple questions regarding these notes.